This is the Strait of Gibraltar. At its narrowest point, Europe and Africa are separated by just 14 kilometers of water. To put that in perspective, a commercial flight covers that distance in under 2 minutes. A high-speed train would do it in 3. And yet, despite sitting at one of the most strategically important crossings on the entire planet, no bridge has ever been built here. There is no tunnel that connects the two continents. No fixed link of any kind has ever survived long enough to open to the public. And it's not for lack of trying. For over a century, some of the most brilliant engineering minds in the world have looked at this narrow strip of ocean and believed, with genuine confidence, that they could conquer it. Every single one of them has walked away humbled. This is the story of why. To understand why Gibraltar has defeated everyone who has tried to build across it, you first have to understand what is actually happening beneath the surface of that narrow channel. Because the water between Spain and Morocco is not just sitting there. It is doing something far more violent and far more strange than most people realize. On one side of the strait sits the Atlantic Ocean, fed by cold currents that pour in from the north. On the other side is the Mediterranean Sea, a body of water that is heavily exposed to the sun, constantly evaporating, and because of that evaporation, extremely salty and dense. When two bodies of water with such a difference in weight and temperature are forced through a narrow gap at the same time, the result is not a simple blending of the two. What actually happens is closer to a collision. The lighter Atlantic water rushes in along the surface, while the heavier Mediterranean water sinks and forces its way back out along the bottom. This creates powerful vertical currents moving simultaneously in opposite directions within the same narrow channel, and those currents are relentless. In 1991, a research vessel called the Nautilus anchored in the middle of the strait with an objective. The crew was tasked with drilling 5 meters into the seabed to collect soil samples that would eventually be used to plan the foundations for a bridge. The drill was lowered, the engines ran, and within minutes the ship was being thrown sideways through the water so violently that the steel cable connecting the drill rig to the hull was stretching to the point of snapping. The captain ordered the cables cut before they tore through the deck entirely. A modern vessel, designed to hold position in rough conditions, could not stay still for even a few minutes. The crew pulled the equipment out of the water and went home. And that was just the water. The seabed beneath it turned out to be an entirely different problem. Before any serious engineering could begin, though, someone had already proposed skipping the engineering entirely and simply draining the sea. It was 1928, and Europe was still recovering from the First World War. Into that atmosphere of exhaustion and rebuilding stepped a German architect named Hermann Zergel, with a proposal that immediately made headlines across the continent, mostly because of how staggering it was. Zergel called the project Atlantropa. The plan was to construct a massive dam across the Strait of Gibraltar, and then, over the course of decades, allow the Mediterranean to slowly evaporate and drop by as much as 200 meters. New land would emerge from the receding seafloor. The exposed territory would be colonized and farmed, and a permanent land connection between Europe and Africa would exist where the strait once stood. Now, the instinct is to dismiss this as the kind of thing you might read in a science fiction novel, and plenty of people at the time did exactly that. But Zergel was not an amateur. The engineering details of the plan were worked out with genuine thoroughness. The problem of how ships would cross between the normal ocean level and the artificially lowered Mediterranean was addressed directly. His solution was a system of locks, massive concrete chambers where a ship would enter, the doors would seal behind it, and the water level inside the chamber would be lowered mechanically until the vessel was at the right depth to continue into the sea. The same basic principle is used today at the Panama Canal. The concept was not inherently absurd. What killed Atlantropa was not a lack of ambition, it was the consequences. Scientists eventually worked through what removing 200 meters of water from the Mediterranean would actually mean for the surrounding coastline. The rich, fertile areas around the sea's edge would become salt flats. Ecosystems that had existed for millions of years would collapse almost immediately. The coastlines of Spain, Italy, Greece, Turkey, Egypt, and every other country bordering the Mediterranean would be transformed into dead zones of dried seabed. The project was quietly abandoned, but the idea of physically connecting the two continents did not go with it. By the late 1990s, attention had shifted back to the more conventional approach of building some kind of structure across the strait. The problem was that no one had yet produced a reliable picture of what was actually at the bottom of the water along the shortest crossing route. When that picture finally came together, it stopped every plan that had existed up to that point. Modern sonar surveys conducted along the 14-kilometer crossing revealed something that genuinely surprised the engineers reviewing the data. Rather than a relatively flat stretch of seabed, the scans showed an enormous underwater canyon running directly between the two continents. The depth at the center of this channel reaches 900 meters. To understand what that number means in practical terms, consider this. The English Channel, which separates England from France, is a maximum of 76 meters deep. The tunnel beneath it, which took years to complete and is considered one of the great engineering achievements of the modern era, was built through rock lying roughly 40 meters below the seafloor. The gorge beneath Gibraltar is more than 10 times as deep. If someone had attempted to build a conventional suspension bridge across the strait at its narrowest point, the concrete piers holding up that bridge would each need to be roughly the height of 3 Eiffel Towers stacked on top of one another, planted in the middle of violent churning currents on a seabed covered in extremely hard, ancient rock. And they would need to remain stable through storms that regularly push wind speeds above 100 kilometers per hour. A tunnel through the rock at that depth was considered and ruled out almost immediately. At 900 meters below the surface, the water pressure alone is sufficient to collapse steel. The rock itself, formed under immense compression over millions of years, is among the hardest materials found anywhere beneath the ocean floor. Drilling through it with conventional tunnel boring machines at that depth, while managing the pressure and the currents above, would have been essentially impossible with any technology currently available. Engineers who had arrived at Gibraltar expecting a manageable challenge left facing something categorically different. And then, sitting beneath all of those obstacles, was the most dangerous problem of all. In 2004, a powerful earthquake struck the Moroccan city of Al Hoceima. Buildings that had stood for decades collapsed within seconds. The damage was severe, and it was a reminder of something that geologists had known for some time, but that had not yet fully registered in the engineering calculations for the Gibraltar crossing. Running directly along the floor of the strait is one of the most significant geological fault lines in the entire region. This is the boundary between the African tectonic plate and the Eurasian plate. These two plates are not stationary. The African plate is moving northward, slowly and continuously pressing into the southern edge of Europe. The force generated by that movement is the same force that originally pushed the Alps upward and continues to cause seismic activity across the Western Mediterranean and North Africa to this day. What this means for any structure built across the strait is not subtle. A conventional bridge spanning the channel would have its foundations split between two separate tectonic plates moving in different directions. In the event of an earthquake, even a moderate one, the sections of the bridge on the African side and the sections on the European side would shift independently. The forces generated by that kind of differential movement would be enough to shear the piers clean off at the base and bring the entire structure down into the water in a matter of seconds. A rigid concrete tunnel would fare no better. Engineers often use the image of a glass tube placed across two conveyor belts moving in opposite directions. The moment one belt jolts, the tube snaps. A sealed tunnel carrying rail passengers at depth, subjected to the same forces, would rupture, and the water would pour in faster than any evacuation could account for. The short route, the one that looked so obvious on a map, turned out to be almost perfectly designed to make construction as difficult as possible in every category simultaneously. Deep water, violent currents, the hardest rock on the seafloor, and an active fault line running directly underneath. For years, the project stalled. Then, in 2005, a research vessel called the Kingfisher set out on a survey that approached the problem from a completely different direction. Rather than studying the 14-kilometer route, everyone had been focused on, the ship moved west into the Atlantic and began mapping a longer, indirect crossing that no previous survey had seriously examined. What the Kingfisher found changed the entire conversation. To the west of the main strait, running along a submerged ridge called the Camarines Sill, there was a potential crossing route that was roughly twice as long as the direct path. 28 kilometers instead of 14. At first glance, that sounds like a step backward, but the seabed along this route is dramatically different. The depth drops to 300 meters rather than 900. And the material covering that seabed is not ancient, hard rock. It is thick layers of clay and soft sediment. The clay itself turned out to be the most important discovery of the entire century-long effort to connect the continents. Soft clay does not behave the way hard rock does during an earthquake. Rock fractures. Rock snaps under sudden lateral stress. Clay compresses and stretches. It absorbs shock. If a tunnel is bored through that clay and the earth moves, the clay surrounding the tunnel walls will flex with the vibration and dampen it, rather than transmitting the full force directly into the concrete structure. Engineers who had previously been trying to find a way to fight the geology of Gibraltar suddenly realized they had found a location where the geology was working in their favor. The decision was made to abandon the direct route permanently. A tunnel bored through clay at 300 meters of depth along the longer western path was not only technically feasible, it was also actually achievable with equipment that exists today. The project was redesigned entirely around this route. In 2023, Spain and Morocco signed an official agreement to resume work on the Gibraltar Tunnel. What is being planned is not a simple tube beneath the water. The current design calls for 3 parallel tunnels running side by side. 2 of the 3 would carry high-speed rail traffic between the continents, with trains moving at speeds exceeding 200 kilometers per hour. The third, positioned between the other 2, would serve as the primary maintenance corridor and emergency evacuation route in the event that anything goes wrong with one of the passenger tunnels. The scale of this project, even along the longer and more manageable western route, is extraordinary. But unlike every previous attempt, it is grounded in a genuine understanding of what is down there and what will actually survive. It is worth sitting with the full arc of what it took to get here. More than a century passed between the first serious proposals to cross the Strait of Gibraltar and the signing of an agreement that might actually lead somewhere. In that time, a ship was nearly torn apart by the currents while trying to take soil samples. An architect proposed removing an entire sea from the map of the planet to create a land connection. A canyon nearly a kilometer deep was discovered directly beneath the shortest crossing point. Earthquakes destroyed cities and reminded everyone that the ground itself is not fixed. And slowly, through all of that, the engineers who kept showing up and kept doing the surveys eventually found the one route where the Earth was not entirely working against them. The first trains through that tunnel are not expected to run until around 2040 at the earliest. That is still a long way off, and there is plenty of history to suggest that delays are always possible when the strait is involved. But for the first time, the path forward is not a theory or an ambitious dream. It is a specific route with known geology at a manageable depth, through material that engineers know how to bore through. For the first time, the 14 kilometers of water that have kept two continents physically apart for all of recorded human history finally has a real answer on the other side of it. It just turned out to be 28 kilometers long. Thanks for following along. If you like our content, feel free to give us a like and a follow, as it helps our channel gain traction and educate more people on some of the best engineering marvels of our time.